Okay, let's begin the second one in terms of artificial intelligence and its integration into the translational clinical research, which includes genomics as well as clinical data and drug discovery, definitely. So, the most event since the first one was most important one was NVIDIA GTC 2026. Well, this was a fantastic event, and there were new publications, new AI update, and I'm happy to share as within next well coffee time in details of these important things so that we all get updated on the things. Those are helping us to accelerate the discovery and innovation into the field of clinical and translational and genomics field. So I think that one of the major thing was that the NVIDIA GTC 2026. So there they have talked about the Verarobin platform, then Proteina complexa. Well, let me just restate even before going in there. This is probably the one of the biggest, or it's definitely one of the biggest event where a, a AI agent or the entire artificial intelligence most elaborate and integrated discussion was shared and most innovative things that was done and will be going to be uh, put as an effort was discussed on this NVIDIA GTC 2026. So let's go like a couple of them. I'm not going in many of them, but I will go one by one. Like Beta Rubin platform. It has been quite an optimization for uh, for the biology, then Proteina complexa, then Pharma GPU reads, Bionemo and Clara. We have liquid biopsy CAR-T, confoundational models, agentic AI, and the reality jowl check. So these are the combination of the AI and the latest work. Those has been very important in terms of the AI integration and others. Let's go to the GTC 2026. Well, I think the term is quite literally spoken here. Janssen's $1 trillion vision. It was an insane event. So Beta Rubin is next generation compete for biological discovery. What it means, in simple thing, 100x approximate improvement for protein folding, 1.7 million protein complex prediction, DGX station for a researcher. Then you have large MOE models, black hole integration, and a lot more other things. I can go in details, but let me just put it like Vera Rubin, and probably you'll get an sense from there. If you see, well, let's relevant to the this one probably better. It's a Vera Rubin platform, and it's been shaping the generation of AI, and you will get all details in there. I'm not branding for the NVIDIA itself, so I'm not going in details. Um, so I was just most interested on this contract, like a state of AI in telecommunications and other things. Well, that's a different discussion. I don't want to go in there, but either way. So you should lead it. It is accelerating quite a bit in terms of the research of our interest. Now, second one is Proteina complexa, 1 million protein binders experimentally screened. This is a huge statement and a leap. When I'm saying a leap, it's really a leap in the field. So if you look at in here, What it does, partially latent flow matching with test time computing computer scaling, generates binder sequence end to end without inverse folding step. That's very important. First ever de novo designed carbohydrate binders. Then PDGFR binding. Well, I love PDGFR. Well, in terms of you are looking for the fibrosis, there are a lot of people interested to look at the PDGFRP and others to look as a marker. Collaborators, they had a lot of them in a rich company. You can find them here and there. But let's just put it on this way, and let's just go a little bit on this. So this is a beautiful protein complexable. Name has a kind of a very fancy dancing speed, but that's a different thing. So, what does it do? It says a noble, fully atomistic protein binder design framework unifying conditional generative modeling and optimization. It has two-part core model development and then a white lab validation. So it has worked on 1 million binder candidate and 133 targets. In collaboration of Manifold Bio, Biba Biotech, Novo Nordisk, Duke University, Cambridge University, and LMU in Munich. Well, I don't know why they are not coming to me. Probably I need to reach out to them. I don't know. So it's one of the early model where you have the AI model, and people keep saying, okay, this is AI, this is AI, this is doesn't have much of the the wet lab application and all of these things. Well, I will be cautious. I have been saying for years, I think 5 years or 6 years, and I have been advocating for a application into our regular research. It's like that. Now we're coming to that exciting moments where we have AI model, and then we start doing the white lab validation and see they have the white lab data. Please read the report. Uh, Read the preprint. It's in here. So let's go through the paper a little bit short. I'm not going in details. Let's go very short. So well, I hope they have it in at some extent. Okay, they have presented in ICLR scaling atomistic protein binder design with generative pre-training and test time compute. Well, they have mostly collaborated with the Oxford University. That's good. I'm jealous. So let's see what they are saying. They are saying in a couple of things actually. Model overview. Let's go in there. So protein complex model overview. So it does three things: a continuous latent protein representation, target condition denoising, and joint sequence, and a structure output without redesign. So figure one, what it is showing? You have fully atomistic input encoder, then you have target condition denoiser. It has couple of things in there, partially latent encoding, decoder, and go on. Then second, we have the protein complex generation and inference time optimization pipeline. I'm promising I'm not going in details. Target conditioned generation of partially latent binder. Then you go to the finally atomistic binder. That's kind of a thing. So let's go a couple of important ones. Visualization of generated binders. Well, it looks good. I mean, at what I say, we have been doing this molecular docking for some time, so, and this one also. I mean, this is good. I'm not going in there. Small molecule binders, enzyme design, inference interface, hydrogen bond optimization, four-class conditioned binder generation, in silico performance, and benchmarking. And they are saying the complex itself, well, novelty, well, it takes 15.6 seconds, and novelty is 0.80. Well, RF diffusion has 0.87. Even the APM has 0.86. I don't know, the one to do with validation. Then small molecule target benchmarking, it's 0.71. So novelty is a little bit less than RF diffusion. And then inference time computer scaling for protein target, you can see. Well, the best in class, in best in search, Monte Carlo treatments, alpha design, bite curve generating. Okay, let's see. Unique success. And then finally they have the AMI notification. So, okay, experimental validation. Let's go in there. Okay, on design specific, on design poly specific. That's fine. Target solved of 127. Well, that's off design, on design. That looks quite good actually. Hmm. Protein complex, self fixed. On design hits and specificity for each method sequence design combination. All specific specificity sequence. This looks good. Well, I don't want to go in like bragging it all about. I'm not presenting that paper, but I think this data looks good, and it could be a game changing things. Let's go to the next part. The pharma GPU arms race. Roche versus Eli Lilly. Well, that's a fight. That's a good fight actually. Eli Lilly. Let's go. The 3500 plus Blackwell GPUs by Roche or Genentech, and Eli Lilly has 9000 plus petaflops. Lilly Potter. They had one. I mean, Blackwell Ultra 1000 plus. And in the Roche, they are using 90% genetic small molecule programs. Hmm. And ban me for drug square digital pathology. I mean, Genentech and Roche is doing fantastic with this AI integration. On the side, Eli Lilly is jumping on a lot, and I think Eli Lilly is the only company people keep saying that you are using AI, you are using AI. What is the output? What is the near-term output? What is the long-term output? There is a lot of conversation around that, but if you look at in here, and then Lilly probably is the only company who already is cutting the cost, substantial cost, by using AI. For example, if you see Lilly, see, well, I hope I find it. How Lilly already using AI to reduce cost. So Lilly is the only company who is already using their major like drug production, process acceleration, and a lot of things, and they're already getting substantial. If you don't go through this, you'll find it. I don't remember the exact news, but as much I recall, I mean link, I don't remember. That's Lilly is the company who is already using the AI and directly accelerating the drug production, and he getting huge benefit. So this is the first case where a company is already getting the output rather than waiting for some time and investment will output someday. They are in real time getting profit. This is a huge milestone. Then let's go a little bit with Bionemo, Clara, and the biology model stack. So Clara, you can just find it in there. Then you have the Clara Generate, Clara Reason, Clara Coda FM, La Pratina, Kermit and BSQSP. Only reason I'm not going in details because it will take insane amount of time, and I assume that everyone doesn't have that much patience to just listen this on the weekend or the first day of the week. But it's a new model, so those helps us substantially in terms of integrating from the CTMRE, MRI, or the RNA model to the 3D protein structure and all of these things. You'll get details in here. Now, in the last first lecture, we discussed about the Genomic Foundation model. EB2, we discussed Alpha Genome a little bit discussed. AlphaFold 2 probably a little bit. Now, there is something that is called Trillion Gene Atlas, so we probably didn't discuss, if I remember it right. So, if you just search it, this is a kind of a game-changing initiative. This is by Basecamp. So let's search Basecamp. Uh, so this is the Basecamp, and they have this initiative called the Beyond Known Biology. Mm. This is a, I mean, the term, just carefully read it, the Trillion Gene Atlas. It's not one, it's not two, it's termed as trillion. You're not hallucinating. Hmm. The Trillion Gene Atlas. We heard about the billion very recently, but it was mostly the. I mean, I remember when the first human cell atlas started, I was so excited, and I'm happy to be with them. And then we have this also this the NIH initiative that's also does a lot of atlas building in terms of hub map and uh, 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 there is a human another atlas which is like Katie Brown from the Indiana University is leading. So there are many part of it that's happening in there. But the Trillion Gene Atlas is something that's probably will change a lot of things. Also, what it does, a simple way if I do it. So it's a partnership in between the. It's a Basecamp in a research initiative, but it's a partnership between Anthropic, the beautiful company, Ultima Genomics, and the PegBio. And it's powered always by NVIDIA AI. I mean, till now, most of them. So, what's their target? Within 2 years they target to take 100 million species worldwide and then do thousand folds of their genetic diversity study, and they want to look at the trillion genes, and which is fantastic. I would love it. I mean, I'm trying to model done my foundation models and everything, but this looks interesting. These are interesting guys. I mean, hopefully that will work out. We'll see. We'll follow up. Okay, let's go next. That doesn't help. Then from interpretation to design, the translational bridge. This is another area where we probably need to work more. Translation to, I mean, interpretation from the innovation to translation. So it's the DNA diffusion for leukemia. Let's go to the original paper. Why took? I mean, it's a shorted in here, but that's fine. Okay, designing synthetic regulatory elements using the generative AI framework for DNA diffusion. So this is their model. I'm not going in details. I don't want to go in detail. Validation interpretation of cell type specific regulatory sequence. So it's going into the cis regulatory mechanism. This is very interesting work actually. This is something that we should look at. System. So generative AI, use all of them and you get something out and then application of it, a normal cell, tumor cell, and there is a too much modeling in here. In short, DNA diffusion diffusion model generate 200 pp synthetic cis regulatory elements with cell type specificity, 5800 synthetic crease validated experimentally, then reactivated axine 1, axine 2. They tried on the B cell aplasia, if I'm right. Um, isn't it? Let me just see. So that could be. Yeah, mm, extra sick. Well, either way, they have, and then AI design regulatory DNA for leukemia. Then programmable expression control opens a new design space for cell state engineering in hematologic malignancy. Well, that's great things. Now let's go. We already banned the GTC, but let's go a little bit basic science and LLMs companies. So let's say start with the more of a pure research. Rather than AI much integration, this is pure ctDNA isolation. This is a fantastic paper and work. Actually, I would suggest you to read about it. And then we have this in vivo CAR-T by CRISPR. This is a very important work. I mean, I don't want to disappoint anyone, This looks very important to me. In vivo CAR T is will be a game changing, especially for the biologists, because I have personally worked with the CAR T, and I think as this AI guided CAR T design one part, and then you have this Nature paper. This is AI CAR design and targeted pathways modulation and has multi-antigen CAR T durability. So this is AI relevant that if you use AI to artificial intelligence to do the CAR T design, so you can get a I mean multi-target agent. So you can read all of it in here. I mean AI is, as I said, the AI is always promising. In vivo site specific integration of this. So if we come to this paper in vivo cytosol engineering, what they have done is that they have okay. Let me just see. So what did they say? Uh, we developed a two-back-to system to deliver CRISPR-Cas9 ribonucleoprotein and DNA donor template using enveloped delivery vehicles and adeno-associated viruses, respectively. Um, and they integrated T cell specific delivery and integrating efficiency vectors together by optimizing them and by integrating CAR transgene into a T cell specific locus. We generate therapeutic levels of CAR T cells in vivo in humanized mouse models of B cell aplasia and hematological and clinic solid malignancies. This is a huge step. Congratulations to the author. Precise work for T cell therapy. These are fantastic work. So these people are from well, quite a bit different places, like University of California and overall. But this is a fantastic work. Uh, this is a game changing thing. This AI design car design, AI guided car design, which I have shown you earlier, and I would welcome you to read this. This will be a very important thing, and we are going into there vastly rather than slowly. And we'll be doing fantastic. Then we have this LLM company update. Okay, I'm not going in their details because actually there are some update, but not that much since the last one. The last lecture, OpenAI had some GPT Mini, Microsoft has some Copilot Health, Anthropic has some Anthropic, yeah, the Trillion Gene Atlas, which we have talked about the base camp. We covered it already. The isomorphic we have discussed earlier. Lecture at isomorphic can always discuss Health AI, Amazons, and all these things we discussed. Agentic AI. This is another game-changing area that we should work elaborately because this is the what do we call it? The trend and voice of the present time. Agentic AI in healthcare, and I myself have developed a lot of them including the foundation models, including the automatic AI. It has so many guidelines. I can give a probably whole day lecture on just the models I have developed on these and a lot of skills and all those things that can be used in any era. For example, if you just go in here, your agentic AI or any of them, if you want, they are should be from like just put them in the clinical side. You want to get them work, just come in here and you take this. For example, this is one of the vital work that's in my contribution in this area. It's not that popular because I don't do much of campaigning, but yeah, that's fine. So this is the universal life science and clinical skills in here, which has a how it works. If you want in there, that's it has a universal point of interaction for all AI models, including the ChatGPT, Cloud, Gemini, Mistral, DeepSeek, or whatever you have in mind. Just connect it. Just download this repository, connect it with them, and then done. Whatever you want. For example, if I go in the skills, and this is the most resource, most intense, rich, authentic collection of research anyone can imagine to do anything in life science and clinical science. I have worked it since very long time to build up these skills for all LMs. So it's 3D genome to the AI agent, then the different type of epigenomics. You have the the clinical science. You have the generative drug designing, genomics, hematology, LLM research, lab automation, oncology, pathology, AI like slide reading, everything, protein designing, proteomics, quantum biotech. Um, it's transcriptomics from single cell, RNA, DNA, attack, site-seq or app-seq, whatever you want to do. Everything is in there. It connects to the, I call it the biomedical operating system. It itself has the skills, agents, and mathematical foundation to run and be an autonomous agent itself. If you convert any AI or anything, that will be autonomously doing everything from the analysis and interpretations and everything that you are asking for. Just give a offline models or anything, or connect with the llama or whatever you want to do. So these are the things that's going into the agentic AI, and that's what I developed. Any agentic AI you have in the market, just connect it in the base, and it will be doing every single damn thing like a professor in those respective field, rather than being a novice who doesn't know anything. Let's go. Igbia AI, Hippocratic AI. Well, that's a probably interesting name. Heidi Health. I don't know. It's Harvard Matt Heidi. Dino Sci-Fi. Okay. So let's just see one by one. A couple of them. I'm not going all of them. I don't have that much energy. Igbia AI. So what they are doing? Okay, introducing BI, your agentic transformation. So clinical, commercial, and different field. That's good. Hippocratic AI. So what is their safest healthcare generative AI agent? Okay, that's what we're looking for. There are so many of them. I'm not going all of these, but I myself has worked a lot of AI agent since the last 5 6 years on building up and applying them in terms of the our in clinical and translational and genomics and all this context. I'm happy to answer anyone's any question. If you have it, just shoot me an email. And then the mighty Tempest AI, I mean, their year-to-year growth is insanely 83.4%. That's 1.27 billion, all their reach. In the meantime, I should have started a company. Um, we were largest pediatric AML registry. Okay, that's interesting because pediatric registry will have a lot of interest. So let's see what they are saying. Temples and Blood Cancer United announce collaboration to develop one of the largest pediatric acute myeloid leukemia real world data registry. That's on March 17, just a couple of days ago. So that would be interesting because those data has quite an implication and you can generate a lot of papers out of these and most importantly clinical insight. That helps a lot. Hmm. So you are welcome to read. They are doing fantastic, and I would love to talk with them sometime whenever they have, or I can host a podcast actually for them sometime. Uh, well, they term it Dare to Dream project. Well, I'm quite here. Ask me people who knows me. Uh, Well, in hematology, couple of publication like physician complementing AI. There is a DNA diffusion, which you talked earlier, Titan, cytodiffusion, random forest, post-transplant model. There are hundreds of paper that's coming. And I love them. I love to read them. These are the couple of limitations we have till now. So that's something we are dealing day by day. It's not like we don't want to deal or something. It's a process, it's a work in progress. There is nothing to be disappointed, nothing to be frustrated in here. Let's go. 5 takeaways from this week. Biology is literally built into NVIDIA, AMD. I mean, AMD in first time is good. So I don't know. I myself is a little bit biased. Biodemo is a good. Protein complex is awesome. Rose CPU is good. These are all great feats, but AI has developed itself in a stage from where it will be in the core of translational, computational, and clinical research and patient cares, and it will be the driving force, the assistant of the modern clinical care and patient care and cure and discovery. Big Pharma GPU race, Eli Lilly versus Roche, that's fantastic. Liquid biopsy, fundamental things, ctDNA that we talked about. Then we talked about the DNA fusions model and all those things, AI designing the car. And then finally, the agentic AI that's been started from the concept to the company's initial enthusiasm and now in real time applications. This is exciting time. There's a couple of references. You can just go through up this week discussion. There are more references. And thank you everyone for listening it till now. It took approximately 30 minutes, but I'm happy to answer either you're an individual, a student, a teacher, someone enthusiastic, someone expert, or from a company want to have a discussion. You don't need to pay for an instance until unless you got a substantial collaboration. But I'm happy to discuss anything, any aspect that helps you, me, and everyone in this field. Anything, any question, just shoot me an email. Thank you. Exciting time ahead.